Item 12.18 of Levine is all about osmotic pressure. Summarized here are the information given to us, and we are now asked to find the following. Letter A, estimate the osmotic pressure of this solution using the Van Hoff equation. And B, given that the observed osmotic pressure of this solution is 7.61 atm, we are now supposed to find the activity A of the water and the activity coefficient gamma of the water in this particular solution. So what we're given here are the following. So you have 0.3 moles of our sucrose, and at a temperature of 20 degrees and 1 atm, this corresponds to a molarity of 0.282 moles per decimeter cube. Also given here is the density of water at 20 degrees and at 1 atm. So for this one, we now try to compute, first for letter A, the osmotic pressure, capital Pi, using our Van Hoff equation. Via several simplifications, we can find our pi easily for ideally dilute solutions. The osmotic pressure pi is simply equal to your CB times RT. CB here refers to the molar concentration of our solute B. In this case, the molar concentration is just the molarity. So I also took the liberty of already converting decimeter cube into liter. So it turns out 1 decimeter cube is equal to 1 liter. Also for the purposes of making sure that our units are consistent, we have to convert gram per cubic centimeter into something that incorporates liter on it. Now it turns out that 1 gram per cubic centimeter is numerically equal to 1 kilogram per liter. So that 0.998 grams per cubic centimeter is actually just equal to 0.998 kilograms per liter. We now use these converted values so that later on we can be sure that everything should cancel out. Now, going back to letter A, we now input the values. CB is the molarity of our sucrose solution. That's 0.282 moles per liter times the universal gas constant. For this one, since our volume is in the unit of liter, we might be tempted to use this value of our R, and we should be correct. The unit here is liter atm per k mole times the temperature, which is 20 degrees, or that is now equal to 293.15 Kelvin. Now plugging in these values to our calculator, we now get the following value. That's 0.282 times 0.08206 times 293.15, giving us our osmotic pressure equal to 6.78. And as for its units, we have to cancel out the units that are here in our expression, so that what we're left with is the unit of atmospheres. So that is for letter A. Now for letter B, we're now trying to find the value of the activity and the activity coefficient of water. Small letter A here represents the activity of our water, and gamma here is the activity coefficient. Given that it is observed that the osmotic pressure is actually 7.61 atm. Now for this one, we need to be able to compute first the mole fractions of our solute and also our solvent in our solution. So for this one, we have to now find X sub B and also your X sub A. To do this, we now go back to our molality for our solute. And for this entire thing, let's just try to assume an amount of water that we have for the solvent. So let's say we assume that we have exactly 1 kilogram of water that is used as the solvent. So from this, we can now compute the number of moles of our sucrose that's present. So since there's 1 kilogram of water that's present, we can now compute the number of moles of the solute NB, and that is simply its concentration in molals times the mass of solvent. So that's now equal to 0.3 moles of sucrose. Now as for your water, since we already know that there's 1 kilogram that's present, we can now try to convert its mass into number of moles by dividing 1 kilogram of water by its molar mass. So for water, its molar mass, we can simply compute it. So you have 1.008 times 2 plus 15.999, giving us the molar mass of water, which is 18.015. So for our water, we have the number of moles computed to be equal to the following. That's 55.51 moles. A side note here. If we go back to our assumption of 1 kilogram of water, we chose this one arbitrarily, although it turns out that 1 kilogram is quite convenient, since from our definition of molality, a molal is equal to mole per kilogram. So this choice of the amount of solvent is quite convenient, but in truth, you can just actually choose any amount of water as as our assumption here. It really doesn't matter what you choose, because later on, the values that you should get here will be used to compute for the mole fraction. You could use instead 100 grams of water here and also for this one, and it will turn out that the values of mole fractions that we'll compute will be the same as if you've used 1 kilogram. So that's our segue. Now going back, let's now compute for the mole fraction of our solute B. So X sub B will be equal to the number of moles of the sucrose divided by the total number of moles. That's 0.3 plus 55.51. Now plugging this into our calculator, we'll get our mole fraction now. That's 0.3 divided by 0.3 plus A, since we stored the number of moles of water earlier. And so we have this value. That's 5.37 times 10 to the negative 3. So once again, we store that value now. And as for the mole fraction of water, we simply take this value and subtract it from 1. So for our water, that's 1 minus x, and that leaves us with a value of 0.995. With the values of the mole fractions already computed for our sucrose and for our water, we now use a different equation for our osmotic pressure, this time using the one that has our activity coefficient in it. So we're also given this particular expression over here. So we have the following. So pi, or the osmotic pressure, is also equal to the negative of the gas constant R times T all over the V asterisk MA. V asterisk MA stands for the molar volume of our solvent A when it is pure. The asterisk stands for a pure substance. Times Ln, the activity coefficient of our solvent A, times the mole fraction of our solvent A. Now at this point, we still have not computed yet the molar volume of our water when it is pure. So to find its molar volume for the pure water, we now use the density that was given to us for pure water at 20 degrees and 1 atm, and we now compute from that our molar volume. We make use of the converted value over here, so that is now 0.998, or no, it should be the other way around. That's 1 liter over 0.998 kilograms. Since again we're looking for the volume, so it should make sense that the liter is in the numerator. Let's convert the kilogram into gram first. And then we multiply this by the molar mass of our water. That way we should be able to get the volume in liter per mole as our molar volume. Canceling out the units, we're left with our desired units of liter per mole, and so we have the following. That's 18.015 all over 0.998 times 1,000. So the molar volume of pure water is equal now to 0.01805 liter per mole. With this already known, as well as the x sub A, we can now proceed to compute for your gamma A, or the activity coefficient of water. So plugging in now, we'll have our pi observed. The pi observed is 7.61 atm. Which should now be equal to negative of the R. That's 0.08206 liter atm over K mole times the temperature of 20 degrees. That's 293.15 Kelvin all over the molar volume of pure water, which is 0.01805 liter per mole, times the natural logarithm of our activity coefficient, gamma A, times the molar fraction of the water, which is 0.995. Now, using our calculator's abilities, we should be able to compute gamma A quite fast, actually. So let's plug this in now. That's 7.61. Equal to negative 0.08206 times 2. Using the shift solve function of our calculator, we should be able to compute the activity coefficient quite easily. So for our water, it turns out that gamma A should be equal to 0.9997. So that takes care of the activity coefficient. As for your activity of the water, so let's get a clean sheet of paper at the back. The activity of the water is simply equal to its activity coefficient times the mole fraction of our water. The activity coefficient we've already computed earlier. That's 0.9997 times the mole fraction of water also computed earlier. That's 0.995. Now multiplying the two together gives us the activity of our water. And for that, we now have the following. So that's 0.997 times Y. And so the activity of water is equal to 0.9943. Going back into this, our activity coefficient is unitless. So that's why we don't have a unit here. And since gamma is unitless, and same with your mole fraction, the activity should also be unitless as well.